Eric Burgess here. Out of school, 70% of students eat lunch and then walk around. 80% eat lunch. If a student is selected at random, find the probability that they walk around given that they eat lunch. Okay, so we have a lot of given this, that, and things are happening. So let's go ahead, just take a second and write down what we're given because there's a lot of words here. So we're told that there's 70% of students and there's all this talk about eating lunch and walking around. So these seem to be our two events. So I'm going to let A equal, this is going to be the event that we eat lunch. So if we eat lunch, that's event A. Event B will be walking around. Walking around. So now that we have A and B, I choose A and B because all our probability formulas use A and B. So we could do that. I could have easily picked other letters like L for lunch and W for walk. Like we could do it that way too. But in this case, A and B will make it easy to translate to our formulas. So we say, okay, and we're told that if they eat lunch and then walk around, so we've got an and here. So this is A and B, that's 70%. So we've got this fancy dancy result. A, the probability of A and B, we're told that's 70%, 0.7. Then we're told 80% eat lunch. Eating lunch is event A. So we're told directly the probability of A. That is 0.8 or 80%. If a student is selected at random, okay, find the probability, okay, that they walk around given that. So given that immediately means we're going to need one of those, vertical line things. So we say probability that they walk around given that they eat lunch. So walking around is event B. So this is what we're looking for, the probability of event B. And then we say given that, that's this vertical line, they eat lunch, which is A. So this is the nebulous thing they want us to find. What is this thing? So we've got an and probability and a probability of A. Now, looking at this, there's something really important we have to decide that the problem sort of leaves up to us, which is, are these events independent or dependent? That matters because the probability of A and B has two formulas, one for an independent case and one for a dependent case. So in the independent case, probability of A and B, well, if they're independent, remember this, that an event is independent if an event A, say given B. So let's just say that this is the probability that you get a heads on a coin flip given that you got a heads before. So this is like a previous thing that happened. So we say, okay, well, you got a heads. Given that you got a heads, are you going to get another heads? And would that change anything about the probability of A? If it does, then the events are dependent. It depends on previous inputs. But of course, we know coin flips, that it doesn't matter how many times you flip that coin, the chance that you get a heads is still 50%. So the probability of A is unaffected by B. They are independent. And if we have the probability of B given A, right, so we're saying, so we flip the letters here and this can throw people off, but remember it's the exact same thing we're saying here. So let's just say that this is the chance that we get the event B, that we get a tails, let's just say. You flip a coin, you get a tails. Does that change anything if before you got a heads? Well, no, the chance of getting a tails is still 50%. The probability of B is not affected by the probability of A. So we can use this to check for independence. And so we notice that that when we do this, the probability of A and B just is the probability of A and B. This stuff doesn't have to be taken into account because they would be independent. They're not affected by prior inputs. So that means that the formula, this is a really long-winded way of explaining the formula, but I see people just use this and they have no idea why it's true, and it can really make it hard to understand what formula you're supposed to use and why when it comes down to the test. So, but that's the exact reason why the probability of A times the probability of B is the independent formula for A and B, because that's exactly what they would be. But if we instead have that there is a dependency, well, the probability of A and B, that it can't be this anymore, because there are cases where A or B could have changed if something previously happened. For example, let's say, what is the probability that you need to use the bathroom given that you just drank 10 gallons of water? I mean, if you can even drink that much, given that you drink a gallon of water, it's going to be a lot higher, right? Because your need to use the bathroom is related to how much liquid you drank. And so for that reason, we'd say, hey, these are dependent events. So we couldn't just multiply them because one might be greatly affected by the other, or even slightly. They're affected by each other. So we say A and B in this case, when they're dependent, that's equal to the probability of A times the probability of, now there'd be a dependency, right? So we'll account for that here, B given A. So we're saying that, hey, that's the probability of A, but if B depends on A, well then that's accounted for here. So we've got a different looking formula for these. And look at this, if it was independent, if it does turn out it's independent, then we'll just get the probability of B here, and that's the exact same thing as what we have here. So I just really want to drive home this point because, again, if you understand this, it makes it easier to understand, what you're supposed to do. So looking at this, we say, well, walking around and eating lunch probably are dependent events. So we're going to use the dependent one. And if it turns out that they're independent, it's fine because this will just wind up being the probability of B anyways. So it's a more conservative way of doing things. So we could say, okay, well here, probability of A and B, well, we have that. That's 0.7. Probability of A, that's 0.8. And then we're looking for the probability of B given A. So all we have to do is solve this formula and we'll find it. So if we divide by 0.8 to both sides, right, these will simplify away to 1. And we get probability of B given A is equal to, we turn this on, 0.7 divided by 0.8 is equal to 0.875. 0.875. And this is our answer. If you have any other questions about this, feel free to drop a comment down below. Subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.